Hello and welcome to LeetCode 2101, Detonate the Maximum Bombs. So, the problem goes as this: you're giving a list of bombs. The range of a bomb is defined as the area where its effects can be felt. There is in the shape of a circle, with the center as the location of the bomb. And it goes basically, you have this range of you're giving a list of lists where every input in the list, every list inside this bombs list consists of the x coordinate, the y coordinate, and the radius of the bomb. And well, as you can see, I've drawn some of this array of bombs here, and well, the maximum bombs that could be detonated here will be 3 because we can start with this bomb, which will then prompt the 6-3 bomb and the 2-2 bomb to be detonated. However, if we started detonating either 2-2 or 6-3, we wouldn't be able to detonate the others. So how can we choose like the first bomb to detonate? At the beginning, you might be tempted to do something like unit set, and just finding like the maximum area that you can get with like this by unifying the area of the bombs. However, there is a simpler solution, and it's by doing a graph. So obviously, we need a way to find if we need a way to find if one bomb can detonate another bomb. And the way to do this is by calculating the Euclidean distance and see if the distance is less than the radius. However, we can see that this is not bidirectional. Like this is like a directed graph because in this example, the 4-3 bomb can detonate the 6-3 bomb, but not the other way around. And so, how do we do this? All right. So with a graph, I already made the spoiler. Well, we can iterate over the bombs and see what other bombs this bomb can detonate. So, for example, for 0, if we're 4-3 located here and the radius is 3, this is the same. We can see that the 0 bomb, the bomb with the index 0, can detonate the other two. So, it has a way to reach either of the other two, but the other one's not. And this is because if we calculate the distance, well, it's gonna be less. It's gonna be less than 1. The distance which is between this. This is gonna be less than 3, which is the radius of the 0 bomb, but it's gonna be bigger than 1. So probably something about 2. And that's how we know that we can get to either 1 or 2 from the bomb 0, the bomb with the index 0. And well, once we know that, once we construct the graph, how do we know what's the maximum number of bombs we can detonate? Well, to do that, we need to compute like the biggest graph that we can like traverse, and usually like it's like the biggest tree, the biggest span tree that you can build with a graph. Obviously, it is not even guaranteed that you can get for to every node. We could have like many graphs, something here like this, some other bombs here, and you can use like 2 propagation algorithms to achieve this. Either breadth first search or depth first search. I personally think depth first search is easier to come with, and since we just want to find the biggest span, it doesn't matter which of the 2 we use. So let's take a look at a better example. Let's say we have these bombs, and And obviously we first need to make the graph, and then we can traverse the graphs in that first search to see what the biggest graph we can build, starting by any of the bombs. So if we build the graph, once we build the graph, by searching, iterating through the distances and seeing which of them are less than the radius of the bomb and within reach of the bomb we're looking at, this is the graph we're gonna get. And to do this is very simple. We just take, like, let's say bomb 1 and compare, we calculate its clearing distance to bomb 2, bomb 3, bomb 4, and so on. So that's gonna take an n square time. It's gonna have complexity of big O of n squared. And yeah, so that's how we get, like, the graph. So we compare bomb 0 to all the other bombs, and then bomb 1 to all the other bombs. And whenever our radius for the bomb we're looking for is less than the distance, then we know we have a connection. So that's actually very intuitive, I think. Maybe not how to do it, not how to come up with it. Obviously, none of this stuff is easy. And well, once we have the graph, we just have to perform that first search, starting at every node. So we can sort of guide with, like, this list graph notation. So if we start 0, we can go to either 1 or 2. If we check the neighbors, then for 1, then we see that we don't have any neighbors, so that's whatever. Then we end that path there. For node 2, we see that we have for neighbors 1 and 3, but we already visited 1, so it's no use to visit it again. We will enter in an infinite loop. For for the other node that has as a neighbor is 3, so then we go deeper. For 3, we also have as neighbors 1 and 2, but we already visited them. And then we end up at node 4. So we already visited all the other nodes. So that's how, yeah. So that's the max depth. Then we don't have any more neighbors to visit. So the way this will work, once we write the code, first here we will have something like a visited set, and then here the visited set will be an empty set. Then we will add 0, and we will go search 1, doesn't have any neighbors. Then we go from 0 to 2, and we will have 1 and 0 as visited. So that's why we won't check 1, because we already visited it. We will have a way to check it. So we visit node 3, and if we want to check its neighbors out, by the time we arrive to node 3, we will have sorry, this is a 0. We will have visited nodes 1, 0, and 2. So the only node that it's a neighbor of 3, but it's not here, is 4. So we will finally visit node 4. And then by the time we arrive here, we will have, like, this sort of visited nodes set. And then we check that none of the 4 neighbors hasn't been visited yet, so we will end the algorithm there. Similarly, if we start, for example, node 2, we will do it with similar path, but we wouldn't check node 0, because we can get from node 0 to node 2, but we cannot get from node 2 to node 0, because 0's node's radius is bigger than the 3. Meanwhile, the radius for nodes 2 explosion is just 2. Now, to code this, we're gonna start by building a graph. In this kind of graph is gonna be a dictionary. Just I mean, it could also be a list, since they are indexed from C, like they are the way to go to a node is just by its index, but we're just gonna use a dictionary for this time. Um, let's also record size of the bombs list. So this is like the size of the this is the number of nodes there's gonna be. All right, so then as we saw, we're gonna in order to build this graph, we have to do an n-square algorithm and just compare one node to the other ones. So yeah, let me go ahead and put this double node. Then we don't want to this double loop. We don't wanna we wanna check one node against itself. So we're gonna skip it if I is equal to j, because that will mean we're comparing the same the one node, one bomb against itself, and we don't want to do that. And well, then we can decompress the bomb's values doing something like this. And we want to do the same for the other bomb we're comparing it with. Right? Well, we're actually not gonna use radius 2 because we can only activate bomb 2. We can only detonate the other bomb if our radius from the bomb we're checking, in this case bomb of I, is bigger than the distance. We don't know, we shouldn't be able to know what the other radius is. Anyway, so yeah, in order to calculate the Euclidean distance, that's just the hypotenuse. And well, if you can see, I import the square function from the math library in Python. And well, this is, I mean, if you don't know how to get the Euclidean distance, this is just how you do it. You calculate the distances of every single component, x to x, y to y. This, and then you do you get the square of that, and then you get the square root. No. Then if our radius from the bomb we're checking with is bigger or equal than this distance, then we know that we can get to detonate the other graph. I mean the other bomb, the jth bomb. So then the graph of I will have will have a connection to J. So bomb I will have a connection to J. And an easy way to do this is every time we're gonna check a bomb, we just make this an empty list. If there is no bombs that connect with this one, we can just leave it as an empty list. It will mean it has no neighbors. But in the case its explosion reaches another bomb, then we just tell it, yeah, it reaches this other bomb. And now, just to do this easier, we'll make another function called depth first search. We will say which node we're currently in and the nodes we've visited, right? And I didn't mention it during the sketching of the program, but the way we can see like the size of the bombs is with these visited nodes. We can check how big this stuff is, and then if it's bigger than the maximum, some maximum, then we just set it to value, and at the end we will visit that one because the length of this visited set is gonna be the largest bomb range bomb like sequence that we can build. Alright, so first things first, obviously if this node is invisited, we just have to wait. There's no way I'm going up, there's no point. This is common the first search point, is just so that we don't enter an infinite recursion loop. And to ensure that this doesn't happen, whenever, if it's not there, since we're just visiting it, then we add it. Alright. Then we will have to visit the neighbors of this node to further expand, and let's just call it neighbor for neighbor in graph of this node we're visiting. We're gonna search recursively with the same set. Remember when we were doing the we want to record everything, so we first search like one branch of the graph and then we search the other branch. We want to keep all the nodes that we visited in that branch, so that we don't do like some sort of circle around the graph. Also, we just to keep count of the nodes we've visited in total. So this is like some memory location where we're gonna locate all the ones of the nodes we're visiting. All right. Then we need some sort of max, right? So in Python you can do max. You can do like max global variables, but I'll be honest, I don't know how to use them, so I always just use lists instead. So max size of 0 is going to be equals to the max of itself. Compared to the size of visited, right? Yeah. So yeah, then we just let me just put this and then I'll explain. I forgot. Well, actually, no, this is alright. Alright. So our global maximum size is it's here, so list. This is just because of the way Python works. If you build a list, then it's sort of global. The scope gets like downstream. As it's just a normal variable, Python cannot tell if you're just declaring another variable or if it's something that was declared before. However, with a list, it's able to tell that this list was built here. Otherwise, why would you be trying to describe the index 0? That's just how Python works. Then, for the per search, as we said, for every node, we check if it was visited. If it's not visited, then we can further expand it and check all of its neighbors. And just perform the search recursively until it has no more neighbors to visit. Then it will return to this point and check the next neighbor and so on. It's important to end the same node just after checking if it's not here. This is like the check we do to ensure. This is the check we do to ensure that it doesn't fall into a loop. And then, once everything's done, we can check if the size of this is bigger. I mean, we could build the set here, pass the set, and then after each iteration, check the length of the set. I think that actually makes more sense. I'm gonna do that. Let's call as for set. And then we pass this empty set, and then we do the same stuff we did here, but with the length of s, which is visited. And this is because after we're done all the visited nodes, I mean, this won't change. The same set is the same for all the downstream there for search. Let's give it a try. And we get an error. Nate 4. Right, just minor mistakes. So you can see this works. And yeah, this same set is gonna be the same for every time we start. The only way this can be different is if we start a different node that we saw in the drawing example. So complexity. We do this stuff, so we have just building the graph is an n-square algorithm. Meanwhile, for performing the depth first search, so in the worst case scenario, this is a fully connected graph, and that will mean we visit every edge, we visit every node, and then for that node we visit every edge and so on. And then like exploring a full graph takes something like an n squared times. Well, I mean, like not exactly, because we have like visited stuff. So we will have like search like node 0, then we go from node 0 to all the other nodes. We add them, but then for each one of those, we will check all of its neighbors, and we will see that we already have those. But since we're for every neighbor, we're checking all of its neighbors once. That's still in square. And since we want to start at every node, this will be an n square, because we just say that this is performing the for such worst case scenario fully connected graph. It's technically n square size. And then by the end, we end up checking this n times. So the worst case scenario is an n cube to the cube, an n cube. Big O of n cubed. As for the space complexity, that's pretty straightforward. This graph fully connected, then it's just an array of size n times n, which is n squared. So this is time and space. We have n squared. And that's it for this problem. There's also a way to do it with breadth first search. Very similar. Maybe take a look at it. Yeah, I think this is it for it. Thanks for watching. I try to do is the dates. This is all daily, so I give it a like if you like it. Whatever. Thanks for watching.